So far in this module, we've covered the goals of the data link layer, framing techniques, and handling errors. Now, we are finally ready to meet our first protocol, Ethernet. Whether you've been aware of it or not, you've probably used Ethernet in the past. Do these cables look familiar? These are Ethernet cables. Ethernet is extremely popular and is the most widely used data link layer protocol, at least where the devices are linked by physical cables. First, some history. The first version of Ethernet was implemented in 1976, and in 1978, a second version arose. TC, Intel, and Xerox worked together to publish DIX, which stands for TC, Intel, and Xerox. This version is also called Ethernet 2. In 1983, with a change that we shall discuss soon, DIX became IEEE 802.3 standard by the IEEE Standards Association. As both Ethernet 2 and IEEE 802.3 are widely used, we shall cover them both. As you'll see, they're almost identical. Usually, both are simply referred to as Ethernet, and we'll do so too after this video. For this video, in order to be precise about what we mean, we'll explicitly state whether we consider Ethernet 2 or IEEE 802.3. Let us consider the Ethernet frame format. We should get used to this kind of drawings, as we'll see many of them along the way. Don't worry if this looks complicated, we'll explain every bit and byte shortly. First comes a preamble of 8 bytes, each containing the bit pattern of alternating ones and zeros, that is 10, 10, 10, 10. In Ethernet 2, all 8 bytes had this pattern exactly. In 802.3, the last 2 bits of the last byte are set to 1, 1. This last byte is called the start of frame. The last 2 1 bits tell the receiver that the rest of the frame is about to start. Sending this bit pattern before a new frame allows devices on the network to easily synchronize their receiver clocks. The preamble is not really a part of the actual frame, it only precedes every frame. Next, we have 2 addresses, each consisting of 6 bytes. We'll describe Ethernet addresses in the next video, but for now, let us notice that a frame starts with a destination address, then followed by the source address. Why would the frame start with the destination address? Is there a reason for that? Well, actually there is. The very first thing a device is likely to do with the frame it has received is checking whether this frame is destined to it or not. If the frame is not destined to this device, it can be simply dropped. Why is this source address important? Well, to know whom we should send a reply to, if necessary. This source address also plays a role in the way some network devices are implemented, as we'll see in future videos. Next comes a quite problematic field, called the type or length field. In Ethernet 2, this field is called type, and it tells the receiver what payload this frame carries. For instance, if this frame carries an IP layer, then the receiving network card should forward the frame's payload to the IP handler. If the frame's payload is ARP, then the ARP handler should deal with it. By handler, I mean the code that handles this protocol, for instance, the code that parses ARP. We'll learn about IP and ARP in the future too. Don't worry about it for now. We'll come back to the need for length and how it is dealt with in IEEE 802.3 shortly. After this field of type or length, we get up to 1500 bytes of data. This number was chosen as RAM was expensive back in 1978, and the receiver would have needed more RAM if the frame had been bigger. This means that if the third layer wants to send more than 1500 bytes of data over Ethernet, it must be sent across multiple frames. There is also a minimum length of data, 46 bytes. Together with the other fields of the frame, the minimum length of an Ethernet frame is 64 bytes in total. Why would we need a minimum frame length? This is not crucial for understanding the Ethernet frame and related to collisions. I've created a separate bonus video for explaining this issue, video number 3.10. You're welcome to watch it, of course. For now, Given that we have a minimum length for an Ethernet frame, what happens if the sender wants to send a very short message, let's say just 1 byte? In that case, the sender has to pad the message, for instance with zeros, until reaching the minimum length. For example, if the sender wants to send only 1 byte of data, such as the letter A, she'll have to add 45 bytes of 0. Last but not least, we have a checksum. This is a 32-bit CRC checksum used to determine whether the bits of the frame have been received correctly, as we've explained in the previous video. In case of an error, the frame is dropped. The CRC is computed on the entire frame, that is, including the header. Notice that it doesn't include the preamble, as it is not really a part of the frame. Remember the term overhead that we've introduced in the previous video? A checksum is a good example of such overhead. It is not part of the payload, but it helps us ensure that the payload has been received correctly. When we use CRC32 for the checksum, we set a fixed overhead of 32 bits, or 4 bytes, regardless of the length of the data. In other words, if we send only 1 byte of data, we get a 32 bits checksum, and if we send 1000 bytes of data, we still get 32 bits of checksum. Now, let's get back to the padding issue. We said that the data field has to be at least 46 bytes long, and if not, we pad it. For simplicity's sake, let's assume we pad with zeros, as the standard indicates. Well, we actually have a problem here. Let's say the sender wants to send a single byte consisting of the character A. So she'll send an A followed by 45 zeros. What happens in case the sender wants to send A and 0? That is, the data actually consists of A0. In this case, she would also send an A followed by 45 zeros, but this time the first 0 is actually part of the data and not the padding. We need a way to differentiate these cases and understand which bytes belong to the padding and which bytes belong to the data in case of a short frame. Ethernet 2 dealt with this problem by, well, not handling it. That is, the third layer will receive the data and the padding, which would be an A followed by 45 zeros in this example, and will then have to figure out on its own which bytes belong to the data and which don't. This is doable, of course, if the third layer includes a length field. However, this solution is far from elegant. Why would the third layer deal with a padding problem that should be dealt with by the second layer? This is a clear violation of our layers model. For this reason, IEEE decided to change the type field into a length field in IEEE 802.3. So, for example, a frame carrying a single byte of data, A, will have the length field set to 1, whereas a frame carrying 2 bytes of data, A0, will have the length field set to 2. This is an elegant solution, but now 2 issues arise. First, if we receive an Ethernet frame, how do we know if it's an Ethernet 2 frame, where this field means type, or an IEEE 802.3 frame, where this field means length? Second, what happens with the type field? How will the receiver know what protocol is carried inside the frame? Let us start with the first question. Just to clarify, by the time IEEE 802.3 was published, many Ethernet cards had already been in use. People didn't want to replace their network cards just because a new standard was published. The solution was to allow both Ethernet 2 and IEEE 802.3 to operate on the same network. Fortunately, all the type values used at the time had greater values than 1500. The solution is thus straightforward. In case this field has a value less than or equal to 1500, it actually means length, and in case it has a value greater than or equal to 1536, it means type. The values in between currently have no defined meaning. For example, if we see a frame where the value of this field is 400, it is clear that we have an IEEE 802.3 frame, which is 400 bytes long. Now you try. In case we see a frame where this field is set to 20, is it an Ethernet 2 frame or IEEE 802.3 frame? Indeed, this is an IEEE 802.3 frame, which has 20 bytes of data, and thus 26 bytes of padding. And in case we see a frame where this field is set to 2000, in this case, we know that this is an Ethernet 2 frame, and 2000 is the type. So this is how we know whether we are dealing with an Ethernet 2 or an IEEE 802.3 frame. Next, how does an IEEE 802.3 frame contain the type information? That is, given that IEEE 802.3 overrode the type field, there was no way for the receiver to figure out what to do with an incoming frame. Thus, IEEE 802.3 adds another header of the LLC, that is, Logical Link Control protocol within the data, which conveys the type information. So an IEEE 802.3 frame will have a destination address field, then a source address field, then a length field, and then an LLC header, followed by the data, and then the checksum. After an Ethernet frame is sent, transmitters will wait a very short period of time before transmitting the next frame in order to allow the receiver to know that the transmission of a frame is over. This idle time between frames is called the inter-packet gap, and this is basically the framing method of Ethernet. In this video, we covered every field of the Ethernet frame. We mentioned the preamble, which precedes the frame. We talked about the destination address and source address fields. Again, we shall elaborate on Ethernet addresses on the next video. We then talked about the type or length field and understood why both type and length are important. This field is followed by the data, which is then followed by padding in case the data is shorter than 46 bytes. Finally, a 32 bits long CRC finishes the frame. So now you know the meaning of all fields of the Ethernet frame, whether Ethernet 2 or IEEE 802.3. If you're interested in more information about collisions and the minimum length of an Ethernet frame, check out the bonus video for this module. On the next videos, we shall dive into Ethernet addresses and then look at Ethernet frames in Wireshark.